As you settle into the gentle quiet of evening, let's begin a journey that starts right here, in this peaceful moment, and gradually expands outward through scales of distance so vast that even light, the fastest traveler in the universe, takes billions of years to cross them. But tonight, we start small, with the most familiar scale of all, the human scale, the foundation upon which all our understanding of the cosmos is built. Right now, as you listen to these words, you exist at what we might call the natural human scale. Your body, perhaps 5 to 6 feet tall, represents the measuring stick your mind uses to comprehend all other distances. When you stretch your arms wide, you span roughly the same distance as your height. This is your personal unit of measurement, developed over millions of years of evolution, perfectly calibrated for navigating the world of trees and rivers, caves and clearings, the scale at which our ancestors lived and thrived. Consider the room around you. Most residential rooms range from 8 to 12 feet in their longest dimension, roughly 2 to 3 times your height. This feels comfortable, proportional, manageable. You can cross such a room in just a few steps, perhaps 4 or 5 strides. Your voice carries easily from one end to the other. This is the scale of human comfort, where we spend most of our lives, where our intuition about distance feels most reliable. But even at this familiar scale, we can begin to appreciate the remarkable precision with which humans measure and understand distance. The ancient Egyptians used the cubit, the distance from elbow to fingertip, as a standard unit. This was typically about 18 inches, and with it, they built pyramids that still inspire wonder today. They understood that consistent measurement was the key to creating structures that would endure. In your own hand, you carry similar natural measuring tools. The width of your thumb is roughly 1 inch, the span of your hand about 9 inches, your pace approximately 3 feet. Moving beyond your immediate space, consider your neighborhood, the area you might walk through on a pleasant evening stroll. A typical city block might be 300 to 400 feet long, about 100 to 130 of your steps. Walking at a comfortable pace, you cover this distance in perhaps 2 minutes. The familiar rhythm of walking gives us another intuitive understanding of scale. We measure longer distances, not just in feet or miles, but in walking time. It's a 5-minute walk to the corner store, or the park is about 15 minutes away. Within this human scale, we've learned to create remarkable things. A football field, 100 yards or 300 feet long, represents a distance that feels substantial, but still comprehensible. You can see clearly from one end to the other. The players appear as distinct individuals, not as tiny figures. This is still within the range where human vision works well, where we can judge distances accurately, where a thrown ball follows a predictable arc that our minds can calculate instinctively. As we expand our view to encompass an entire town or small city, we begin to approach the edges of what we might call the extended human scale. A town of 50,000 people might stretch 3 or 4 miles across, a distance that would take an hour to walk, but still manageable in a day's journey. From a high hill overlooking such a town, you can see its entire extent, understand its layout, comprehend its boundaries. This is perhaps the largest scale at which humans can still feel a sense of complete understanding and control. The fascinating thing about the human scale is how it has shaped our language and our thinking about all distances, no matter how large. We describe vast cosmic distances in terms of familiar human experiences. We say space is empty because we're used to air, to substance, to things we can touch and feel. We imagine traveling to other stars, unconsciously thinking in terms of journeys we might make on Earth, even though the reality is so far beyond human experience that our familiar concepts break down entirely. Our measurement systems, even our most sophisticated ones, trace back to human scales. The meter, the fundamental unit of the modern metric system, was originally defined as 1/10,000,000th of the distance from the Earth's equator to its pole, an attempt to base measurement on our planet itself. But in practice, it was measured using human tools, human techniques, human ingenuity. Even now, when we define the meter in terms of the speed of light, we do so in a way that keeps it close to the familiar human scale, close to the pace of human steps, the size of human rooms. As you lie there in the gentle darkness, consider how this human scale has been the launching point for every great discovery about the size of the universe. Ancient Greek astronomers, like Eratosthenes, figured out the size of the Earth by measuring shadows in 2 different cities. They used the most basic human tools, sticks, shadows, walking distances, to comprehend something far larger than any human could directly experience. Yet they started with the human scale, the length of shadows at noon, the distance a person could walk in a day. The tools we use to explore the cosmos, from telescopes to spacecraft, are still built to human scale. The largest telescopes have mirrors perhaps 30 feet across, large by human standards, but still something we can walk around, something whose size we can appreciate by comparing it to familiar objects. The Hubble Space Telescope, which has revolutionized our understanding of cosmic distances, is about the size of a school bus, large, but not incomprehensibly so. Even our most ambitious space missions, like the Voyager probes now traveling beyond our solar system, are about the size of a small car, built by human hands, guided by human intelligence, working at human scales. This is the beautiful paradox of cosmic exploration. We use human-scaled tools and human-scaled thinking to comprehend scales that dwarf human experience by factors of billions or trillions. We are like ants trying to understand the size of continents, except that we've succeeded remarkably well. The ant, after all, cannot conceive of a continent, but humans have learned to conceive of galaxies. What makes this possible is our ability to create chains of understanding, to build from one scale to the next through careful measurement and mathematical reasoning. We start with what we can directly experience, the distance we can pace off, the time it takes to walk somewhere, the angles we can measure by pointing our arms at different stars. Then we use these direct measurements to infer larger distances and use those larger distances to infer even larger ones, building a ladder of understanding that eventually reaches to the edge of the observable universe. But it all starts here, at the human scale, with human curiosity and human wonder. As you drift towards sleep tonight, you might reflect on how remarkable it is that a species like ours, creatures whose personal experience is limited to distances we can walk in a day, has learned to measure the age and size of the entire universe. We carry within ourselves the measuring tools that have unlocked the deepest secrets of cosmic scale, our pace, our reach, our vision, and most importantly, our restless desire to understand what lies beyond the familiar boundaries of our everyday world. The human scale is not just our starting point, it's our constant companion on this journey through cosmic distances. No matter how far we travel in imagination, no matter how vast the distances we contemplate, we always return to human scale analogies to make sense of it all. We describe the emptiness of space in terms of how few atoms we'd find in a volume the size of a room. We compare the energy output of stars to the combined power of all human civilization. We measure the expansion of the universe in terms of how much a familiar distance would stretch over cosmic time. Tonight, we've established our foundation, the human scale that makes all other scales comprehensible. As you rest here in your human-sized space, breathing at your human rhythm, existing in your human moment of time, you carry within yourself the remarkable ability to conceive of distances that stretch beyond imagination. The warmth of your blankets, the familiar dimensions of your room, the comfortable weight of your body against the mattress, these are not limitations, but launching points for understanding infinity. Sleep peacefully in this knowledge that human beings, despite our small size in the cosmic scheme, possess something extraordinary: the ability to measure, to wonder, and to comprehend scales of distance and time that dwarf our physical existence. We are the universe's way of knowing itself, starting from the simple, profound foundation of human scale experience. Tomorrow's journey will take us to our first destination beyond the human scale, our planetary home, where we'll discover that even the familiar Earth beneath our feet holds surprises that will stretch our understanding and prepare us for the vast cosmic distances that await. But tonight, rest secure in the foundation we've built together, the human scale that makes all cosmic understanding possible. Sweet dreams, fellow measurers of infinity. Our planetary home. Tonight, as you rest in the quiet comfort of your familiar space, we take our first journey beyond the human scale. Not to distant stars or galaxies, but to something seemingly close and familiar: our own planet Earth. Yet even this first step in our cosmic journey reveals distances and scales that stretch our comprehension, preparing us for the vast leaps that await us among the stars. Imagine, if you will, that you could step outside, not just your room or your town, but outside the entire experience of standing on solid ground. Picture yourself floating gently in space, just far enough from Earth to see it whole, a blue and white marble suspended in the cosmic dark. This perspective, first achieved by human eyes only a few decades ago, reveals our planet's true scale for the first time in human history. Earth is vast beyond our everyday experience. To walk around its equator would require a journey of nearly 25,000 miles, a distance so great that even if you could walk continuously at 3 miles per hour, it would take you more than 8 months of constant motion. This is roughly equivalent to walking from New York to San Francisco and back again 4 times. Yet from space, Earth appears as a single, perfect sphere that you could cover with your outstretched thumb. This is our first encounter with the humbling mathematics of cosmic scale. The very planet that seems infinite when we're walking across its surface. The planet whose horizons stretch beyond our vision, whose mountains and oceans define the limits of our direct experience, is actually a small, finite object that light can circle in just 1/7 of a second. But let's approach Earth's size more gently, building our understanding from familiar foundations. Think of your hometown, perhaps stretching 5 or 10 miles across. Now imagine 2,500 such towns laid end to end in a straight line. This gives you the diameter of our planet, about 8,000 miles from one side to the other. It's a distance that would take a commercial airliner flying at 500 miles per hour 16 hours to traverse. When you fly from one coast of a continent to another, you're covering roughly half of Earth's diameter, experiencing firsthand a significant fraction of our planet's true size. The ancient Greeks were the first to measure Earth's dimensions with remarkable accuracy, using nothing more than shadows, geometry, and human ingenuity. Eratosthenes, working in Alexandria over 2,000 years ago, noticed that on the summer solstice the sun shone directly down a deep well in the southern city of Syene, casting no shadow. But in Alexandria, 500 miles north, vertical objects cast distinct shadows at the same moment. By measuring the angle of these shadows and knowing the distance between the cities, a distance measured by human footsteps and the reports of travelers, he calculated Earth's circumference to within a few percent of the modern value. This achievement represents something profound about human consciousness and our relationship to cosmic scale. A person standing in Alexandria could see, at most, 20 miles to the horizon on a clear day. Yet using mathematics, careful observation, and logical reasoning, Eratosthenes comprehended the size of an entire world. He transformed local human-scale measurements into global understanding. This is the same fundamental process we use today to measure the distances to galaxies billions of light years away. As you settle deeper into the tranquil rhythm of evening, consider the remarkable structure of our planetary home. Earth is not just a ball of rock spinning in space, but a complex, layered world with its own vast internal architecture. The crust beneath your feet, the solid foundation that feels so permanent and substantial, is actually just a thin shell, proportionally thinner than an eggshell compared to the egg inside. If Earth were shrunk to the size of a basketball, the crust would be thinner than a piece of paper wrapped around its surface. Beneath this thin crust lies the mantle, nearly 2,000 miles thick, where rock flows like thick honey under immense pressure and heat. Deeper still, almost 2,000 miles below the surface, lies the outer core, a sea of liquid iron and nickel, circumcision in patterns that generate our planet's magnetic field. And at the very center, under pressure millions of times greater than what you feel lying comfortably in your bed, sits the inner core, a sphere of solid iron about 800 miles across, spinning slightly faster than the rest of the planet, hot as the surface of the sun. These are distances that dwarf human experience, yet exist right beneath us. The deepest humans have ever drilled into the Earth is about 7 miles, barely a scratch on our planet's surface, proportionally equivalent to the thickness of a coat of paint on that basketball. Yet we know about these hidden depths through earthquake waves that travel through the Earth's interior, revealing its structure just as light reveals the structure of distant stars. The scale of Earth's surface features also stretches our terrestrial perspective. The Pacific Ocean, our planet's largest feature, spans more than 10,000 miles, wider than the entire diameter of the Earth itself when measured across its broadest point. To fly across it takes nearly half a day in a modern airliner. Its deepest trenches plunge 7 miles below the surface, deeper than Mount Everest is tall. If you could somehow drain all the world's oceans and stand on the deepest ocean floor, the water above would form a column reaching twice as high as most commercial aircraft fly. Mount Everest itself, that towering pinnacle that represents the ultimate terrestrial challenge for human adventurers, rises 5.5 miles above sea level. This sounds modest until you consider that if you were standing at its base and wanted to reach its summit, you would need to climb a vertical distance equivalent to stacking more than 1,500 three-story houses on top of each other. The air at its peak contains only 1/3 the oxygen available at sea level, so thin that human lungs struggle to extract enough to sustain consciousness. Yet, even these extremes of terrestrial geography are tiny compared to Earth's full dimensions. If our planet were perfectly smooth, covered by ocean of uniform depth, that ocean would be only about 1.7 miles deep everywhere. A thin film of water on a large sphere. The difference between our highest mountains and deepest ocean trenches, those dramatic variations that dominate human geography and challenge human endurance, represent less than 1/10 of 1% of our planet's diameter. As you rest there in the gentle darkness, breathing the thin layer of atmosphere that sustains all terrestrial life, consider that this atmosphere extends upward for hundreds of miles, gradually thinning until it merges imperceptibly with the vacuum of space. Yet most of the air you're breathing right now, the oxygen entering your lungs, the nitrogen that makes up most of each breath, lies within just 3 miles of Earth's surface. If Earth were that basketball we imagined earlier, all the breathable air would form a layer thinner than the fuzz on the ball's surface. The International Space Station orbits about 250 miles above your head, not really very far by planetary standards, less than the distance between many neighboring cities. Yet this relatively modest altitude is enough to provide a perspective that transforms understanding. From that height, astronauts see the entire curvature of Earth, watch lightning storms flicker across continent-sized areas, observe the thin blue line of atmosphere that protects all life, witness 16 sunrises and sunsets every day as they circle our planet every 90 minutes. This orbital perspective reveals Earth's motion in a way impossible to sense from the surface. Right now, as you lie still and peaceful, you are actually racing through space at tremendous speeds. Earth spins on its axis at about 1,000 miles per hour at the equator, faster than the speed of sound. Yet this motion feels like perfect stillness because everything around you shares the same movement. It's as if you are in a smoothly cruising car with perfectly tinted windows, unaware of your speed through the landscape. But Earth's spin is just the beginning of its cosmic dance. Our entire planet orbits the Sun at roughly 67,000 miles per hour, a speed so great that Earth travels nearly 1.6 million miles through space during a single day. In the time it takes you to sleep for 8 hours tonight, Earth will have moved more than 500,000 miles along its orbital path, carrying you and everyone you know on a journey through space, longer than a trip to the moon and back. These planetary speeds, incomprehensible by human standards, give us our first taste of the scales we'll encounter as we venture further into the cosmos. Yet they also reveal something beautiful about our cosmic situation. Despite hurtling through space at thousands of miles per hour, Earth provides a stable, nurturing environment where you can lie peacefully in your bed, where delicate flowers can grow, where butterfly wings can carry their owners on gentle flights. Our planet is simultaneously a cosmic speedster and a gentle haven, a contradiction that speaks to the elegant balance of forces that make terrestrial life possible. The measurement of Earth's true size marked humanity's first great leap beyond direct human experience into astronomical scales. It required thinking beyond the evidence of our senses, trusting mathematical reasoning over immediate perception, imagining a whole that no single human perspective could encompass. This intellectual leap, from the local to the planetary, prepared our species for all the greater leaps that followed. From ancient navigators first sailed beyond the horizon, they carried with them the hard-won knowledge that Earth was round, that there was more world beyond what any one person could see. They trusted mathematics and measurement over the apparent evidence that the world was flat, that distant places didn't exist. This was perhaps humanity's first act of cosmic faith, believing in a reality larger than direct experience suggested. Tonight, as you rest on the surface of this remarkable planet, you're participating in that same tradition of cosmic faith. You're trusting that the measurements and calculations of scientists reveal truths about our planetary home that your direct senses cannot perceive. You're accepting that the solid, motionless ground beneath you is actually the surface of a spinning sphere racing through space at impossible speeds. You're embracing a reality far stranger and more wonderful than everyday experience suggestions. This is the essential skill we need for comprehending cosmic scale, the ability to hold two truths simultaneously, the truth of immediate, comfortable, human-scale experience, and the truth of vast, dynamic, cosmic-scale reality. Earth feels solid and still, and it is also a spinning sphere hurtling through space. Both perspectives are valid, both are necessary for complete understanding. As you drift towards sleep on this cosmic carousel, take comfort in knowing that Earth's vast size and tremendous speeds work together to create the stable, peaceful environment you experience. The planet's great mass generates the gravity that keeps you comfortably in place. Its rapid spin helps distribute heat from the sun, moderating temperatures and creating the weather patterns that make terrestrial life possible. Its high orbital speed maintains the perfect distance from our star, neither too close nor too far, for liquid water and comfortable temperatures. Our next journey will take us beyond even Earth's generous boundaries to explore the solar neighborhood, the realm of planets and the sun, where distances stretch not just thousands of miles but millions, where light itself becomes our measuring stick. But tonight, rest peacefully on the surface of our remarkable planet, feeling the gentle pull of gravity that keeps you safe, breathing the thin atmosphere that sustains all terrestrial life, secure in the knowledge that you inhabit a world perfectly sized and perfectly positioned for the miracle of human consciousness. The solar neighborhood. Tonight, as we continue our gentle journey outward through scales of cosmic distance, we leave behind the comfortable boundaries of our planetary home and venture into the solar neighborhood, that vast realm of planets, moons, and space that surrounds our sun. Here, we encounter distances so large that our familiar Earth-based measurements begin to lose their meaning, and we must learn to think in entirely new units of scale. The journey from Earth scale to solar scale distances represents perhaps the most dramatic leap we've taken so far. If Earth seemed large when we imagined walking around its 25,000-mile circumference, consider this. The distance from Earth to our Sun is nearly 93 million miles, a gap so vast that you could line up almost 12,000 Earths in a row to bridge it. This distance is so fundamental to our understanding of the solar system that astronomers have given it a special name, 1 astronomical unit, or AU. It becomes our new measuring stick for comprehending the cosmic neighborhood around our sun. To begin appreciating this solar-scale distance, imagine that you could somehow drive to the sun in a car traveling at highway speeds of 60 miles per hour. Even if you could drive continuously, never stopping for food, sleep, or fuel, your journey would take more than 177 years. If you had started this impossible road trip when the United States was founded, you would still be driving today, not yet halfway to your destination. Light, traveling at 186,000 miles per second, the fastest speed possible in our universe, takes more than 8 minutes to cover this distance. This 8-minute light travel time gives us another way to think about solar system distances. The sunlight warming your face on a bright day actually left the sun's surface 8 minutes and 20 seconds ago. When you watch a sunset, you're seeing the sun not as it is at that moment, but as it was when you were probably still going about your afternoon activities. This delay becomes our first encounter with a concept that will become crucial as we venture into truly cosmic distances. The time it takes for light to travel reveals the scale of the universe. Within our solar neighborhood, different planets orbit at different distances from the sun, creating a family of worlds spread across billions of miles of space. Mercury, the innermost planet, orbits at about 0.39 AU from the sun, meaning it's about 36 million miles away, or roughly 40% of Earth's distance. Even this close planet is so far that light from the sun takes about 3 minutes to reach it. Mars, the subject of so many human dreams of exploration, orbits at an average distance of 1.5 AU from the sun. But because both Earth and Mars orbit the sun at different speeds, the distance between our worlds varies dramatically. At its closest approach, Mars is about 35 million miles from Earth, still nearly 1,500 times the distance around our planet. A radio signal to a Mars rover can take anywhere from 3 minutes to 22 minutes to arrive, depending on the planet's positions. As we venture outward from the inner rocky planets, we enter the realm of the gas giants, where distances stretch our imagination even further. Jupiter, the solar system's largest planet, orbits at an average distance of 5.2 AU from the Sun, about 484 million miles. This massive world is so far away that sunlight takes 43 minutes to reach it. If you lived on Jupiter, you would see the sun rise and set almost 3/4 of an hour after someone watching the same solar events from Earth. Saturn, the ringed jewel of our solar system, lies even farther out at 9.5 AU, about 886 million miles from the Sun. Light from the Sun takes an hour and 24 minutes to reach Saturn, and Saturn's reflected light takes that same amount of time to reach us. When you admire Saturn through a telescope, you're seeing rings and moons that existed in their observed configuration nearly 3 hours ago in solar time. The outer reaches of our solar neighborhood stretch far beyond the visible planets. Neptune, invisible without a telescope, lies at 30 AU, 2.8 billion miles from our home star. Light from the Sun takes 4 hours to reach Neptune, and Neptune's light takes 4 hours to reach us. But even Neptune doesn't mark the true edge of our solar neighborhood. Far beyond lies a realm of icy bodies called the Kuiper Belt, and beyond that, the Oort cloud, a spherical shell of comets that may extend as far as 100,000 AU from the Sun, nearly 10 trillion miles away. As you settle deeper into the evening's tranquility, consider the profound implications of these solar system distances. The space between planets is not empty like the air around Earth, but neither is it filled with matter. It's a near-perfect vacuum, so empty that if you could somehow create a box the size of your room anywhere in interplanetary space, it might contain only a few dozen atoms. Yet this apparent emptiness is crossed by invisible streams of particles flowing from the sun, the solar wind that creates auroras when it interacts with Earth's magnetic field. These vast solar system distances reveal the remarkable precision required for space exploration. When engineers plan a mission to Mars, they must calculate trajectories across millions of miles of space, accounting for the gravitational influences of multiple planets and the changing positions of worlds in their orbits. The fact that humans have successfully sent spacecraft to every planet in our solar system represents a triumph of mathematics and engineering across scales that dwarf human experience. Tonight, as you rest within our solar neighborhood, you're orbiting our ordinary star at exactly the right distance for liquid water and comfortable temperatures, part of a family of worlds that includes gas giants with dozens of moons, ice worlds with underground oceans, and rocky planets where the conditions for life might exist. The sunlight that warmed your skin today traveled 93 million miles through the vacuum of space to arrive at precisely the right intensity to sustain the complex chemistry of terrestrial life. But as vast as our solar neighborhood seems, it represents only the beginning of our cosmic journey. Beyond the distant comets of the Oort cloud lies something even more profound, the realm between stars, where distances become so large that our astronomical units become as inadequate as miles worth of measuring planetary distances between the stars. As we continue our journey outward through cosmic scale this evening, we now venture beyond even the vast boundaries of our solar neighborhood into the realm between stars, distances so immense that astronomical units become as inadequate as inches would be for measuring continents. Here, in the realm of interstellar space, we encounter the true meaning of cosmic emptiness and begin to grasp why the universe is a far stranger and more spacious place than our earthbound intuition could ever suggest. To understand the scale of interstellar distances, we must first truly comprehend what we mean when we speak of a light year. Light, traveling at 186,000 miles per second, fast enough to circle Earth more than 7 times in a single second, covers almost 6 trillion miles in 1 year. This distance is so vast that if you could somehow lay dollar bills end to end to span 1 light year, you would need more than all the money that has ever existed in human history, multiplied by millions. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri star system, located approximately 4.24 light-years from Earth. This means that the light you might observe from Proxima Centauri tonight actually began its journey toward your eyes more than 4 years ago. When you look at our nearest stellar neighbor, you're seeing it as it existed when you were 4 years younger. A powerful reminder that looking out into space is always looking back in time. To truly appreciate this distance, imagine that our entire solar system, from the Sun out to the orbit of Neptune, could be shrunk down to the size of a US quarter, about 1 inch across. On this scale, Proxima Centauri would be another quarter located about 4.5 miles away. The space between these quarters would be almost perfectly empty, a void so complete that if you could somehow travel at the speed of light, it would take you over 4 years to cross from one quarter to the other. This cosmic emptiness is both beautiful and profound. In the space between stars, a region larger than our entire solar system might contain fewer atoms than exist in a single breath you take. Yet this apparent nothingness is crossed by light from distant stars, carrying information about worlds we may never visit, suns that may harbor planets, perhaps even life. The emptiness is not truly empty. It's filled with possibilities, with radiation, with the faint whispers of distant cosmic events. The journey to our nearest stellar neighbor would represent the ultimate test of human technology and patience. The Voyager 1 spacecraft, humanity's most distant emissary, has been traveling for over 45 years and has covered about 0.002% of the distance to Proxima Centauri. At its current speed, Voyager 1 would take roughly 75,000 years to reach our nearest stellar neighbor, a span of time longer than all of recorded human history. Beyond Proxima Centauri, our stellar neighborhood becomes even more sparsely populated. Sirius, the brightest star in our night sky, lies 8.6 light-years away, twice the distance to our nearest neighbor. The light you see from Sirius began its journey to your eyes in the mid-2010s. Vega, the brilliant blue-white star, is 25 light-years distant. The light you see from Vega began its journey to your eyes in the late 1990s, carrying information about a star as it existed when you might have been learning to use the early internet. As we survey more and more of our stellar neighborhood, a remarkable pattern emerges. Stars are scattered through space like islands of light in a vast dark ocean. The typical distance between stars in our region of the galaxy is about 5 light-years, meaning that if you could somehow visit every star within 50 light-years of Earth, you would find roughly 2,000 individual star systems scattered across a sphere of space so large that light takes a century to cross from one side to the other. Within this 50 light-year sphere around our Sun, astronomers have discovered hundreds of planets orbiting other stars, worlds that might be rocky like Earth, gas giants like Jupiter, or entirely new types of planets unknown in our solar system. Some of these exoplanets orbit within their star's habitable zone, where liquid water could exist on their surfaces. The light from these distant worlds, reflected starlight from planets dozens of light-years away, represents some of the faintest signals humans have ever detected, photons that have traveled for decades through the emptiness of interstellar space to reach our telescopes. The measurement of interstellar distances required a revolution in human thinking about the cosmos. The first successful measurement of stellar distance wasn't achieved until 1838, when Friedrich Bessel detected the tiny apparent motion of a star as Earth orbited the Sun, a shift so small that it's equivalent to observing a quarter from a distance of 3 miles and detecting that it has moved by the width of a human hair. As you rest in the peaceful evening, consider that the very atoms in your body were forged in the nuclear furnaces of ancient stars, scattered into interstellar space by stellar explosions, and eventually incorporated into the cloud of gas and dust that collapsed to form our solar system 4.6 billion years ago. You are literally made of star stuff, atoms that have traveled across interstellar distances and cosmic time to become part of your living, breathing, thinking existence. The light from distant stars that you might see on a clear night has traveled for years or decades through the near-perfect vacuum of interstellar space to reach your eyes. Each photon represents a tiny messenger from another world, carrying information about temperatures, compositions, and conditions on distant suns. When you observe the night sky, you're receiving mail that was posted years ago from cosmic neighbors you will never visit, but can still study and understand. Yet even these vast interstellar distances, which dwarf our solar neighborhood, represent only the beginning of cosmic scale. Our stellar neighborhood itself exists within something far larger, our entire galaxy, the Milky Way, containing hundreds of billions of stars scattered across distances that make even interstellar space seem small. Our galactic island. Continuing our cosmic journey this evening, we now step back from individual stars and their vast separations to contemplate something almost beyond human comprehension. Our entire galaxy, the Milky Way, a rotating island of hundreds of billions of stars, so immense that light takes 100,000 years to travel from one edge to the other. From your peaceful vantage point here on Earth, the Milky Way reveals itself as a faint band of light stretching across the darkest night skies, a ghostly river of starlight that ancient peoples interpreted as a pathway for souls or the backbone of the night. What you're seeing when you observe this Milky Band is actually our galaxy viewed edge-on from within, like looking at the edge of a vast cosmic disk from our position embedded within it. To begin comprehending the scale of our galactic home, Imagine that each star in our stellar neighborhood, those suns we just explored, separated by distances of several light years, is like a single house in an enormous city. If individual stars are houses, then our galaxy is not just a city or even a country, but an entire continent filled with stellar neighborhoods, each containing millions upon millions of stellar homes. The Milky Way contains between 200 and 400 billion individual stars. The true magnitude of our galaxy becomes clear when we consider its dimensions. The Milky Way is a spiral galaxy, roughly 100,000 light-years in diameter. To put this in perspective, the light you might observe tonight from the most distant stars visible in our galaxy began its journey toward Earth around the time humans were first developing agriculture and settling into permanent communities. We live within this cosmic disk, roughly halfway between the galaxy's center and its outer edge, in what astronomers call the Orion Arm, a minor spiral arm containing our Sun and several thousand neighboring star systems. Our location within the galaxy is both privileged and humble. We're situated in what some astronomers call the galactic habitable zone, neither too close to the dangerous radiation-filled galactic center, nor too far out in the sparse outer regions where heavy elements necessary for planet formation are rare. We orbit the galactic center at a distance of about 26,000 light-years, traveling at roughly 500,000 miles per hour in our cosmic orbit. Yet even at this tremendous speed, it takes our solar system approximately 225 million years to complete one orbit around the galaxy. Since life began on our planet, Earth has completed perhaps 20 full orbits of the galaxy. The center of our galaxy, hidden from our direct view by intervening dust clouds, contains wonders that stretch the imagination. At the very heart of the Milky Way lies a supermassive black hole containing roughly 4 million times the mass of our Sun. The galactic center region represents an environment almost unimaginably different from the space around our Sun. Here, stars are packed millions of times more densely than in our stellar neighborhood. Most of our galaxy's stars exist in the spiral arms that wind outward from the central bulge, creating the elegant spiral pattern that we can observe in similar galaxies throughout the universe. Our Sun and solar system are currently located between two major spiral arms, the Sagittarius Arm and the Perseus Arm, in the relatively peaceful Orion Arm. This region experiences fewer supernovae, less intense radiation, and more stable conditions conducive to the long-term development of planetary systems. The spiral structure reveals the Milky Way's dynamic nature. Far from being a static collection of stars, our galaxy is a rotating, evolving system where new stars are constantly being born from collapsing gas clouds while older stars age and die. The spiral arms mark regions where star formation is particularly active, where massive young stars shine brilliantly before exhausting their nuclear fuel and exploding as supernovae. As you rest there in the tranquil darkness, consider that you can sometimes see our galaxy's structure directly. On the clearest, darkest nights, far from city lights, the Milky Way appears as a luminous band stretching across the sky, revealing the edge-on view of our galactic disk. The darker regions within this band are vast clouds of cosmic dust that block the light from more distant stars, creating shadows against the stellar backdrop. The measurement of our galaxy's true size and structure represents one of the greatest achievements in the history of astronomy. The breakthrough came when astronomers studied globular clusters, dense spherical collections of ancient stars that orbit our galaxy like cosmic satellites. This revealed that our solar system was not at the center of the galaxy, but rather located in its outer regions, and showed the true scale of our galactic home. The Milky Way also exists within an even larger structure called the local group. a gravitationally bound collection of more than 80 galaxies, dominated by three large spiral galaxies: our own Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The Andromeda Galaxy, located about 2.5 million light-years from us, is actually approaching the Milky Way and will eventually merge with our galaxy in approximately 4.5 billion years. As you lie there peacefully, you might reflect on the profound implications of your galactic citizenship. Every atom in your body was forged in the nuclear cores of ancient stars that lived and died within our galaxy over billions of years. You are not just made of star stuff, you are made of Milky Way star stuff, assembled from atoms that have traveled thousands of light years and billions of years to become part of your temporary human form. The Milky Way represents perhaps the largest structure that humans can truly comprehend, while still maintaining some sense of community and connection. It's vast beyond everyday imagination, yet it's our cosmic home, the galaxy that contains all the stars visible to the naked eye, all the stellar neighborhoods we might someday explore, all the cosmic history that has led to our existence. But even our magnificent galaxy, with its hundreds of billions of stars spread across 100,000 light-years of space, represents just one small part of something even more vast, the observable universe, containing an estimated 2 trillion other galaxies, each an island universe in its own right.